All right, let's try this out. So I just got a dot cam. Let's see if we can record lecture this way. Okay, so let's talk about 6.3 trig equations part 2. Um, basically, this section is going to talk about how to solve trig equations that involve double angles, half angles, and things of that nature. But if you follow along with the same steps as what we did in 6.2 when we talked about trig equations, the first time, then you'll really be fine here. There's really nothing else to it. So that is if you do it the way that I was doing it. If you do it the way your book did it, then you have to modify your approach a little bit, which is why I don't really care for the way the book does it. Um, anyway, I'm going to give you a couple examples of this, just of my own kind of invention, I guess, although they're not like really, complex equations or anything. But I'll give you a couple examples of my own, and then the remaining examples will come straight from your textbook, so that you can look at the solutions in the textbook. If you want to try that out, see if you like it better. But anyway, let's look at a couple examples. So let's solve some equations. Let's do sine 3x equals 1/2. Okay, so if you think back to what we did yesterday when we were trying to solve trig equations, the idea was that we wanted to try to solve for the trig function and then apply one of three facts, depending on whether you had a sine, cosine, or tangent function. In the case of a sine function, we said that, if sine theta equals k, then that means theta is sine inverse of k, right, plus 2n pi, or theta is pi minus sine inverse of k plus 2n pi. Or in the case that you're working with degrees, of course, you would say, theta is sine inverse of k plus n times 360, or theta is 180 minus sine inverse of k plus n times 360. Okay, so just the equivalent when working with degrees. Anyway, I'm going to work in radians just like I did on the last section, and so we have sine 3x equals 1/2. So this is already in this format, only theta is 3x, right? So you're going to say 3x equals sine inverse of 1/2, or 3x equals pi minus sine inverse of 1/2, okay? So 3x equals sine inverse of 1/2 plus 2n pi, or 3x equals, I'm going to run out of space, but 3x equals pi minus sine inverse of 1/2 plus 2n pi. Now sine inverse of 1/2 we can do in our heads, right? Sine inverse of 1/2 should be pi over 6. So we're going to say 3x equals pi over 6 plus 2n pi, or 3x equals pi minus pi over 6 would be 5 pi over 6 plus 2n pi. So now our goal is, of course, to solve for x. So at this point, we need to divide through by 3. Okay, so if we divide through by 3, we get x equals pi over 18 plus 2/3 n pi. Okay, or you could say like 2n pi over 3, or 2 pi over 3 times n, or whatever. Okay, or x equals 5 pi over 18 plus 2/3 n pi. Okay, so now if you're looking for all of the solutions to this equation, right, all of the solutions are going to be of that form, pi over 18 plus, I don't know, what's a better way to think of this? Maybe we could say 2 pi over 3, maybe we'll say 2n pi, or 2 pi times, I don't know, 2n pi over 3, or 5 pi over 18 plus 2n pi over 3, where n is an integer. Okay, now if you're only interested in the solutions that live in the interval 0 to 2 pi, well, then you do the same trick as what we did when we were in 6.2, right? You just take turns plugging in numbers for n, right? And then you only take the solutions that fall within this interval, right? So for example, if I were to plug in -1 for n, I would get pi over 18 minus 2 pi over 3. That would be less than 0, so I'm not going to include that solution. If I plug in 0 for n, this whole term just goes away and I get pi over 18. That's definitely within the interval, so that's one of my solutions. If I plug in 1 for n, I get pi over 18 plus 2 pi over 3. So I'm just going to use my calculator instead of thinking about getting common denominators and all that stuff. 2 pi over 3. So pi over 18 plus 2 pi over 3 is 13 pi over 18. Now, if you're thinking about when do we know to stop? Well, we know when to stop whenever we get past 2 pi, right? 2 pi would be the same thing as 36 pi over 18. Okay? So whenever we get to 36 pi over 18 or beyond that, we know that we've gone too far. Okay? So this is when I plugged in 1 for n. If I plug in 2 for n, then I get pi over 18 plus 4 pi over 3. That's 25 pi over 18. I'm still inside of the interval. If I plug in 3 for n, I get pi over 18 plus 6 pi over 3. That's 37 pi over 18. That's too far. Okay, so these are all the solutions that are generated by this first rule. Okay, and then I have some more solutions that are going to be generated by this second rule. When I plug in 0 for n, I get 5 pi over 18. When I plug in 1 for n, I get 5 pi over 18 plus 2 pi over 3. That's 17 pi over 18. When I plug in 2 for n, I get 5 pi over 18 plus 4 pi over 3. That's 29 pi over 18. And remember, what I can't go over is 36 pi over 18. Okay, so if I go one more, if I plug in 3, I get 5 pi over 18 plus 6 pi over 3. That's 41 pi over 18. That's more than 36 pi over 18. So that does it for that one. Okay, and so there's my solution set. Okay, you can see that you end up with a whole bunch of solutions. All right, and the problem with doing it the way that the book does it is that the way the book does it is it'll find, like, it'll solve something like, it'll say, it'll say 3x has to equal pi over 6, or it'll basically say this, right? 3x has to equal pi over 6, or 3x has to equal 5 pi over 6. But then it won't include the 2n pi. And you're just supposed to kind of have to reason out that because you've tripled the angle, there's going to be triple the number of solutions or whatever. I don't know. I just don't like the way that the book does it. Again, you're welcome to look at the solution in the book if you like, but I think this is a much more straightforward way to solve the problem. Okay, so there are all the solutions that live in the interval from 0 to 2 pi. These are all the solutions. There are infinitely many of them, right? But the ones that live between 0 and 2 pi, you're going to have 6 of those. Okay, so I'll start a new video to look at another example.